So good morning, everybody. Hope you're having a fine day so far. So I want to spend a little more time trying to finish up the slides for Chapter 4 this morning, and I'm going over a growing perpetuity. I'm on slide 86, and a growing perpetuity is the perpetuity we saw already previously, but this time it's not just C divided by R. As in previous slides, but there's a growth rate. So basically, your payment's going to increase at a rate G. So, for instance, you can endow a college fund and tell them, well, I'm going to increase the payment every year. So here's the equation for the growing perpetuity. Unfortunately, it's not built into Excel. The interesting thing to note though is that we can use a present value in a simple way here, the function in Excel, and trick it a little bit to do it, or we can just do this math in a simple way and just do the subtraction and divide these two numbers. It's actually quite simple. But I want to show you in this example, here's an example of a growing perpetuity, okay, and basically here's the standard equation we originally saw. And I'll just highlight that for you right here. Here's the standard equation, and we just simply the payments are the payment would be $30,000 a year at 8%. How much does have to be contributed today for it to go on forever? Well, since it's not in Excel, we can trick Excel a little bit, right? And as I did before, I can go over to here, which I already did. And the rate is 8%, as you see, and the payment was $30,000, and you notice I made that negative. Well, I tricked Excel and said it may not be infinite payments, but I told it 999, and that's pretty close to infinity. And you can clearly see that the answer comes out to just what's in the slide, $375,000. So that's one way around it if you don't want to deal with the simple, division. All right, so there's another example. So now that's the simple, and then they turn around in the same example, and they say, okay, we're going to increase it by 4% thereafter. So now you notice they do the 4% subtraction here. So all you really have to do is go to Excel and change the interest rate that I had here. Just change that to 4, right? 8 minus 4 is 4, and you'll notice it comes out to $750,000, and I'll just say okay, and that is just like they get over here, $750,000. So I'm just using Excel to kind of trick Excel, and you can get that answer if you don't want to do that, like as I said, the simple math. All right, so here's another similar problem. And again, they start out at 4%, and then they have a growth rate of 2%, and basically it's $100,000 a year that you're going to supplement someone's pay. So the required donation has to be $2.5 million. But if you want a growth rate of 2% every year, you now have to have you need $5 million to endow the chair. So this you can see you're going to start at 100,000 and then just increase by 2% a year. So that's 0.04 originally minus 0.02. So again, you could just use Excel and just put 100,000 for the payment and 0.02, and I'll try that. Let's see if I can do that here. I'll make this 0.02, and I'll make this minus 100,000. Whoops, hold on. That should be 0.02, and it's you can see it's very, very close to $5 million here. Maybe I have to add another 9 here. I don't know. Let's see. There you go. So now we have $5 million. There you go. So that's, again, you can just trick Excel into thinking it's forever. All right, so the next thing we have is called a growing annuity. So today's topic is kind of growing things, right? We have a growing annuity. So this is the present value of a growing annuity. Growing means you start to add more money to your annuity as you get raises, as an example, right? That's the growth rate. And again, unfortunately, this is not built into Excel, and we have to use this equation here, and it's kind of, I can't basically trick Excel into using this equation. It really doesn't work exactly, so I won't try to do that. So here's an example of retirement savings with a growing annuity, and she starts with $10,000 a year, and as she gets raises, she hopes to increase her savings by 5% per year. So you'll have to plug into that equation, and here's what the present value will look like of the payments as they grow for 30 years. As you can see, here's the first year, here's the 30th year, and unfortunately we have to use this equation here, which I don't like doing, but we really don't have a choice. And you'll end up with the present value of this growing annuity is going to be $150,463. All right, then we basically can take that present value and then future value that single amount. You notice that's a single amount forward 30 years, and the future value of her growing annuity will then be worth $2.625 million. Again, we have to use two equations here because we don't have a choice. There may be plugins we can use in Excel for these growing annuities, but I don't see them offhand here. And here's another exact same example, and it starts out at 8% with a 3% growth rate. And I'll go back here, right? You're going to increase your annual contributions by 3% for the next 45 years. So here's that equation again, and here's the second equation for the future value that we have to use. And I wouldn't worry too much about these because I don't want you to have to memorize equations if you can't use them in Excel, but it's just good to see them. All right, so we went over these spreadsheet problems already, and there's an important function here that I want to show you, an equation, and this equation encompasses all the equations with all the functions we saw, and you will see this equation again in when we do bonds in Chapter 6. This equation, including present value of a bond payment, is going to be seen again shortly. So don't worry about it, because it's all going to be, this is all built into Excel, and you'll have no trouble seeing that. And I'll show you all that. All right, so we saw all these already, and I kind of went over these last time, how to do future value in Excel. You notice there's no growth. This is not a growth problem here. And here's more. Excel, and we kind of went over these, and you can see how to get the future value here. All right, and we kind of went, I believe we went over this problem already. You have a choice of paying $20,000 for a car, or making or pay $500 a month for the next 4 years. Which is cheaper to do? Which one will save you more money? And you'll notice that the present value of the payments is $21,290. So you're better off, they say, making the $20,000 payment. However, they don't talk about paying the $20,000, having invested that $20,000. All right, so the last couple of things is, how do we determine the loan payment on a particular loan? So you'll notice here, here's a new equation that's just been solved for the payment itself. And that's quite simple to do. We don't have to worry about that equation ever again, because we go into Microsoft Excel here, and here they are solving the equation for the payment, $9,394. However, you don't have to deal with that. You go into Excel, and I would bring this up, and let me just say okay to that. And I'll go to a new box here, and I'll type PMT and say go, and there's the payment function right there in Excel. That's the payment function. So I say okay, and let me just get these numbers here again, and I'll pop them in. 48.5 and minus 400,000. .5%, 48, and what did I say? 400,000 is the present value. So this will just give us the payment, and this is good to know. And there's the 900,934, just as in the slide. This is a great function to know about, because if you do take a car payment or a mortgage payment, any type of loan, you could pretty much determine what your payment's going to be based on the principal you're going to borrow. So I just say okay, and there's the payment, $9,394. All right, and you can see that that's right here. So again, here's another one, another monthly payment problem. All right, I will talk about internal rate of return when we get back to meet again. This is a little more complicated, and I think it needs some further discussion. And just simply, internal rate of return is the equation or the value when the net present value equals 0. And I'll say more about that when we meet. Again, though, this will be built into Microsoft Excel, so let me just briefly show you that we won't have to worry about that either. And I'll go over to here, and I'll type IRR and say go, and there it is right there. And you can see we'll plug into 2 boxes. That'll be it. So when we meet, I'll say more about internal rate of return, because there's some complications with that and net present value. So so that's really, in a sense, internal rate of return is also the rate function in Excel. You can also use, let me go here for a minute, there's a function called rate, which is also the internal rate of return. And I'll say more about rate and internal rate of return again when we meet. But I just wanted to make you aware that they are in Excel, so we don't have to worry too much about calculating them. And so I believe that's really about it. There's a couple of examples here, and we'll go over that. All right, so we can also solve for the number of periods in a savings plan, and there's a function in Excel called NPER, and that's right here. And I can just show you that. I bring that up, and I'll say NPER and say go, and there it is right there. And we just pop all the numbers here, and we'll get the number of periods. And you see what it says here. It says returns the number of periods for an investment based on periodic constant payments and a constant interest rate. So again, that's in Excel. So we don't have to worry about that. The only ones we have to worry about really with equation-wise are the growth payments, and I wouldn't give that too much consideration. All right, so that's about it. So if you have any questions, again, get back to me, and I will start moving probably tomorrow into Chapter 6 on bonds, and we'll start discussing bonds a little bit. Okay, Hope everybody has a good day.